Hello. Good morning, good afternoon. Can you hear me? You can answer in the question tab. Yeah, perfect. Thank you. We are going to wait just a few minutes more as all the participants can join us. Hi, everyone. We will start now because it's already 3 minutes past. Good morning, good afternoon. My name is Maël Palab, and I am the product manager of Isatis Neo Mining Edition. We are together for half an hour, and today I will present a webinar about the management of extreme values in Isatis Neo. You will have the opportunity to write your questions at the end, and I will be very happy to answer them with my colleagues. Tomorrow, you will receive a recording of the session. Isatis Neo is the new software developed by GeoVariances, a French company that has been dealing with geostatistics for 35 years. It has comparable functionalities with Isatis, but all our clients have said that it is easier to use and user-friendly. The dataset I'm using comes from a real gold deposit, but I have lightly changed the values of the samples. The aim is to show the tools that will help you decide if grade capping is necessary and choosing the capping value. I will show you the exploratory data analysis and the capping tool. I will also show you how to cap during the neighborhood definition. The demonstration will finish through the comparison of two estimations, with capping and without. I am going to consider only high-grade outlier, so I perform a top cut on the values. You can do the same with a bottom cut for very low values. So, to cap or not to cap? The management of very high-grade values is a well-known and complex issue for mining companies. There is no perfect way to deal with them, no globally accepted solution. The challenge is to keep the best from the assay without introducing bias in the estimation. The proper interpretation of outliers in a dataset is crucial to estimate a mineral resource that is representative of the deposit. We can easily imagine the impact of very high values on the global mean and then the variogram. If we keep high values in the estimation process, the risk is overestimating the grades, and so the metal quantity in the deposit. During the recovery process, you will realize the huge gap between what you were thinking you will earn and what you actually get. This difference affects the economic viability of a mining project and, at worst, may sink a company. Conversely, if we remove the outliers, the risk is to miss an economically viable project. Therefore, you need to decide what to do with these outlier values. You need to limit their impact according to the risk you want to take. So, because we are not talking about outliers, let's recall first what is an outlier. An outlier is an observation that appears to be inconsistent with most of the data value. It is an absurd or extreme value that stands out from the crowd. It means that the distribution is globally regular, but some identified samples have a very different value from the others. Having outliers is very common in data distribution. I will now show you a demonstration with Isatis Neo. So I just quit the, okay. So you are now watching the main interface of Isatis Neo. Here you have the data. So this is my gold data set. And here is a 3D view. I will now show you the exploratory data analysis. So I can show that. Okay, so here are the gold assay. On this part, we can see the histogram, and here are the statistics for the gold. We can see the histogram is a very skewed histogram with a long tail of high values. What I want to mean is the mean is 0.5 ppm, but we have some values that are above 100 ppm. So we can see it's very asymmetrical. A small fraction of sample are very high grade. With the exploratory data analysis, you can highlight sample. For example, I take this one. And did you see in the 3D view, they just turn into blue triangles. So, oops. These blue triangles correspond to the sample I just highlighted in the histogram. I can pick one, for example, this one, and I can have the sample number and the name of the drill hole. So this is the drill hole 102, and this is the sample 10,848. So then I can, for example, check it in the data table. So it was this one, the 10,848. So you see it is highlighted in the data table also if you want to find the samples and study them directly. And we can see here the grade of this sample is much higher than all the other grades because it's 19. So I can also, when I select my samples here, so they turn blue here, but we can see the statistics. For the moment, the mean of the total distribution is around 0.5, and the standard deviation is 3.5. But I can then mask the samples, so they turn into red triangles in the 3D view, and the statistics have been recalculated. We can see the mean is now only 0.4 and the standard deviation is 1.7. So it has been recalculated because I did the highlight. So the graphics are here connected. And yeah, the mean and the standard deviation, they decreased because we have made the distribution more stable. So I can just unmask the points also. If I unmask all points, yeah, there is nothing highlighted now, and the statistics are for the global distribution. So now you have seen how to find an outlier on the histogram, and to find it in the data table. We want to know if this very high value is a real measure value or is it a mistake, because mistake can occur during the drilling or sampling of the rock, but also by the laboratory performing the assay, or simply during data entry. But it's very often to have mistakes. Usually, the procedure for each outlier is to check the core sample from a geological point of view and determine if the high value is plausible. Geologists will need to study the surrounding samples. Then you can also use the quality analysis, quality control, QA/QC, performed by the laboratory on the assay. For example, if the duplicate of a high-grade value has the same high-grade value, it is probably correct. If the value is confirmed to be erroneous, the sample should be removed from the database or flagged as undefined. If the value is correct, we will keep the sample in the database, and if you have a doubt, it is generally better to keep the sample. For my case study, I will assume that the erroneous value have already been removed. I will now show you the capping tool. So I close this one, and the capping is here. Okay, so this is the capping tool that is in Isatis Neo since February. Common industry practice is to apply capping on the grade values to limit the potential economic influence of very high grade. So this is the method I am going to show you now. You have to enter the data table and then the variable you want to study. So I have chosen the gold. And here you can choose the number of classes for the histogram. On the top right part, there is the histogram, exactly the same that we already saw. And you can see, for example, here there is some little holes in the distribution above 50 and around 70 and 90 and a lot after. So we can see them. We can also change the number of classes to increase the accuracy. Okay. And so we can zoom. Okay. So here the gold is always in ppm, and we can see that it seems to be quite continuous to 20 ppm, but around 21, 22, 24, there is some little holes in the distribution. This means that there is less samples, and actually there is no sample on this class. So this can be a criterion to choose the capping value. You can say, okay, here we don't have any sample between 21 and 22. So maybe we should cap at this with 21 as a value. So you can also use the NP plot. This is to compare the gold distribution on the x-axis and the Gaussian distribution of the cumulative density function, which is the theoretical function, theoretical curve. And what people usually do is to find the steps. So what I mean by steps is here, for example, oops, we can see there is a brutal transition, a vertical transition. So this is the steps, and if you have a big step, it can be the reason to choose the capping value at this particular value. So we will check a little bit more around here. Yes, there is some little steps here around 50, but yeah, you need also to find a capping value according to the risk you want to take. So if you take a too big value, it can be not really accurate. So we will mostly for this time use the histogram as I showed you before, and then you can choose the capping mode. For example, if you want to perform the top cap or the bottom cap. So I will do the top cap, as I already said. And you can choose the percentile that are a proportion of the distribution in percent, or you can use cutoffs that are capping values. So this is the value of the gold grade, and this is in ppm. I will choose this one, and they will be on the x-axis, like here. The statistics for each capping value is printed on the table here. So we have the capping value, the percentile, but also the mean standard deviation, the coefficient of variation, and the metal loss. If you choose to perform a bottom cap, you will have the metal gain. And on the right part of the graphic, the bottom right part, we have the capping graphs that show the impact of capping on different statistics on the mean, the standard deviation, the coefficient of variation, and the metal loss. You can move from one to another just by clicking on it, and it changes interactively all the graphs. So here we have a capping of 20 ppm. I can choose this one. So it's 1 ppm, and on the histogram, we see the red capping value has moved also. So yeah. The common practices are to keep a coefficient of variation less than 1.5, but for my gold dataset, it's not really possible, because if I choose 1.5, which will be around here, we will have a capping value of 0.5 ppm. So we will cap too many samples, because the recommendation we give you is to cap less than 2.5% of the distribution. If you cap too many samples, you will introduce too many bias in your estimation. So yes, we will keep the 25 ppm as a capping value, and you have the capping value written here, and the new variable that will be created, the name will be gold less or equal to 25 ppm. So this is an automatic naming that makes you save time and not having a database very disorganized. And when you are happy, you press run, and you have the new variable that have been created here in the same data table as you have your input variable. So the capping is a very, it's a decision-making tool that helps you choosing the best capping value for your data. Now I will show you the variograms I created. So there is the variogram of the gold data without any capping, and we can see the nugget effect is around 8, and it's a very erratic variogram. The seal is around 10, and yeah, for short distance, it's not really good. Whereas when I choose the capping variable, the gold less or equal to 25 ppm, we instantly saw that the nugget effect is much lower. It's around 2.5 and the seal is around 3. So this is because the experimental variogram is very sensitive to high values, and with the kpid variable we have a smooth variogram. So the capping made the variogram more stable, and that is what we want for accurate estimation. I have performed kriging on the two variables, the gold grade and the gold with the capping. And I have estimated on a block model. So I will show you the results here. I did a grid of 50 per 50 per 10 meters. So this is the result. This is the result for the gold without any capping, and we can see that it's variable but not too much. And this is the gold with capping. I can show you better in a section. So yeah, this is a section of the block model I just show you. Okay, so this is the result of the gold, the input data. And for example, we can see there is a orange blocks in the middle here. So this means in this part, the block is estimated to contain between 5 and 10 ppm of gold. And if I show you with the capped variable, the orange blocks, they reduced, the size reduced. So, and it turned into light green. So the block that was estimated before to be between 5 and 10 ppm, when you apply a capping, it is now with an estimation between 1 and 5 ppm. So the mean of the block, the estimated block, changes, and it changed, but it reduced because of the capping. So now I can also show you if I print the statistics. So I just right click here and I said variable statistics. On the application messages, we have the statistics for the gold. No, I didn't want this one. I wanted the one of the block model. Yeah. So this one, I print the statistics, and the mean is 0.35 and the variance is 0.3. And if I do the same with the kpid value, the mean is a little bit lessened and the variance reduce a lot. So we can say that the estimation with the capping reduce the mean and reduce the variability also. Another approach is also to restrict the neighborhood of the very high value during the estimation process. So you can do that with Isatis Neo at the neighborhood definition step in the kriging. So I will show you quickly the kriging here. So I put the gold on my grid. And for the kriging here, there is some little option tabs, and one is the capping. So now I will. Okay, we can see here the results of the kriging. And if I apply a top cut, I can replace or ignore. I will replace the samples that are above 15 ppm if they are more than 20 meters far. So if I apply again, yeah, one block change this one. So if I don't have any top cut, this block is orange, like between 5 and 10 ppm. And when I apply the top cut, it turns into light green, so between 1 and 5 ppm. So the top cut during the neighborhood definition may also help you to do capping on your variable. So there is an impact on the estimated block model. I will go back to my PowerPoint. So then, to summarize, the management of high-grade values is generally done applying capping to limit the impact on the economic viability of a mining project. As I showed earlier, the choice of capping value is crucial. However, we need to keep in mind that the truncated distributions may generate a bias in the estimates. Thus, it is not recommended to systematically apply capping. Some geostatistical methods, such as multiple indicator kriging and the top cut model, have been developed to reduce the influence of extreme values without losing the variability of the distribution. The multiple indicator kriging has been available in Isatis Neo since February. The goal is to calculate quantities, estimates, or grade tonnage variables from a macro variable containing indicators at different values of a variable. The probabilities defined by the kriged indicators are interpreted as proportion of the blocks. The top cut methods developed by the Geostatistics Center of the Paris School of Mines will also be implemented into Isatis Neo. Just to show you quickly the top cut methods, it is based on the spatial structure of the grade to see if there is a border effect from low to high grade. So you first have to define an indicator. This is the first graphic that selects the grades above a certain cutoff. Then you will apply a co-kriging of the grades and the indicator. You combine the results, and if you see the third graphic, this is just an ordinary kriging of the grade. The high values in red are concentrated near the highest grade samples. And the last graphic, which is the result of the top cut methods, we can see that the excess metal above the cutoff is spread out near all samples that are above the cutoff, rather than being concentrated near the highest grade samples. So, and we keep more information also. Finally, for projects where production data is available, reconciliation of the block model against production should be used to guide decisions about the handling of outliers. So the presentation of the capping is now finished, and for those who don't know us, I will present quickly the company GeoVariances. So GeoVariance is an industry leader in geostatistics, and we have a partnership with the Center of Geostatistics from the Paris School of Mines. We have more than 35 years of experience and more than 40 experts and consultants that are working with us. There is the main office in France and also office in Perth, Belo Horizonte, and Santiago. We have consultants that can help you for resource estimation and classification or drill hole spacing optimization. So do not hesitate to contact us if you need. You can also attend courses. So there is online courses, mostly in this moment, but also presential in different parts of the world and on different subjects. So you can see them also in the website of GeoVariances, and you can email us to have more precision. Here you can have an overview of the principal companies we are working with. So there is big mining companies, but also consultant services. If you want to know deeper the software, you can have a demonstration. You can contact Marie-Cécile Febve with the email address on the screen, and she's a senior geologist. And this is the end of the presentation. So thank you for your attention. Please, when you leave, you will have a form to complete, so fill it, please. And this is no time for questions. So I will be here with my colleague David Berry, who is an expert geostatistician working from Perth, Australia. And you can now write your questions and we will answer them. So go on. Thank you very much.
So can people hear me, Mael?
Yes.
Okay, so we have a question from Eduardo Takafuji, who asks, can we use capping on the log values? Maybe a log transformation would help define the gaps in the distribution. Not directly in the grade capping interface itself, but there is a calculator tool in Isatis Neo that allows you to take a log of any variable that you want, and you could then apply on those and sort of find your appropriate cutoff in log space, and then sort of unlog the data afterwards manually. And there's also a question from Eduardo: can we choose the capping with declustered data? And Mael knows the software better than me, but from my look at the software at the interface, it looks like there's no option to put declustering weights in there. So we'd have to take that one as a request.
Yeah, you can't now use a declustered weight. No. But you can do declustering before or after as you want.
So we've got a couple of, one is a comment from Renius. There is a standard practice of cutting based on the standard deviation, e.g. Plus or minus 2 standard deviations. I suppose there's quite a few practices out there in different parts. Gavin asks, what do you mean limiting the capping to less than 2.5% of the distribution? So basically, the idea there is you're not changing the values of more than 2.5% of your samples. So that would be choosing a capping value greater than the 97.5 percentile. Now, obviously, that's just a rule of thumb. There's nothing magical about 2.5% or 97.5. It's just a common practice in the sorts of deposits that were discussed here. Vic Singh asks when the Journal method, I think it might be a Rivera method, so I think that's the top cut method that Mail spoke briefly about at the end of her presentation, and I'm not sure if it'll be its own interface or if it'll just have all of the tools necessary for it. The final missing piece to do the procedure manually is going to certainly be in the September release of Isatis Neo. And you could certainly build the procedure then to, it's just a currently missing option in the variography. I'm not in charge of the product development on the software itself, so I'm not sure if there'll be a point and click interface for it. Vic also asks if there are plans for local capping distributions, and I don't know if there are.
Not yet, yeah.
Yeah, that sort of thing, I suspect you would have to script yourself. The Python calculator would allow you to, if you've got a bit of Python skills, to be able to handle these sorts of questions. But we haven't had that request before, as I recall.
No, but we keep it in mind.
Yeah. Masa asks, can we use this software during geological mapping or geochemical exploration? I don't know exactly what the target use cases there are, and so maybe Mail is a better place to answer that question.
Yeah, I don't also really know what you want to say, but yes, you can use it during exploration. Yeah.
Renius asks, what's your take? I think that's referring to the rules of thumb about plus or minus 2 standard deviations. I wouldn't rigorously hold to any particular rule. You know, the fact that, I mean, if you have perfectly normally distributed data, you will, and you've got like 1,000 samples, you will have some more than 2% or 2 standard deviations away from the mean, and there's nothing wrong with those values. They're just part of the distribution, and you should keep them. It's only when they, or at least I would say, it's only when they're quite a long way away from the rest of the distribution that they start to cause problems. So I wouldn't be dogmatic about anything, and I would sort of err on the side of capping less. But if you're working in gold deposits all the time, you probably have a different sort of set of experiences than if you're working in iron ore, for instance, where just the shapes of the distributions change, are just very different in the two commodities. Mm-hmm. So I wouldn't say yes, follow this rule every time. I would always sort of look at the data and try to understand what it's saying, and are the sort of high or low values really part of the distribution or not?
Yeah. Yes. The main thing is these figures are just to remind you that you have to keep in mind you are changing the values of some samples, so you should not do that for too many samples. Yeah, because if you change it too much, you are changing your distribution, and so you will have a really biased estimation. Do you have other questions, or is it all good for you? And you can also contact us by email if you have any questions in the next few days. Okay, thank you very much for your attention, and see you next time for a next webinar. We don't know when, but you will have an email. Goodbye.